Hello, everyone. Thank you and welcome for joining today's webinar, Particle Classroom Series 2, the Basics of Laser Diffraction. My name is Julie Chen Nguyen, and I'm going to be your host today. It gives me a great pleasure today to introduce you our speaker, Dr. Jeff Bodycomb. He is our product line manager for particle characterization. He got his PhD in material science and engineering from Rutgers University. He's also our particle classroom series speaker. Okay, Jeff, the floor is yours.
Okay, great. Well, welcome to the virtual floor, I guess. So I'm Jeff Bodycomb, and today we're going to talk about the basics of laser diffraction as an introduction to the topic. So first, I'm going to try to give you a little perspective of what we're talking about today. I have a performance graph shown here. You see this in a lot of my talks, where I have particle size across the bottom as a diameter in microns, and kind of resolution of mixture components when you have a mixture in a single sample, and then various techniques and applications marked more or less where we think they kind of fit on that size and resolution. And sitting right in the middle with the longest blue bar is laser diffraction, running from really nanometers, well, tens of nanometers up to millimeters, and the HORIBA LA960 and LA350. As you go larger, you'll start looking at image analysis techniques and items such as the cam sizer. And as you go smaller, you'll look at either probably the SC100 and dynamic light scattering. But today we're going to kind of hang out in this tens nanometer to millimeter range. So the first question is kind of why particle size? Why are we doing this? I like to remind myself and everybody else what we're here for. And those of you who learn about the topic, this is kind of suspecting you're in one of these areas and it's going to come up. Really, the particle size affects behavior of materials and the behavior of the materials in processing across a number of industries, from ceramics, oil, rubber, batteries, food and drink, pharma, and so on. An example I like to give, because it's kind of easy to envision, is if I set a chunk of aluminum on your desk that's kind of 10 centimeters by 10 centimeters by 10 centimeters, it just sits there and does nothing. But if I were to give it to you as a 1 micron powder, you would have a very hot time, as it's quite hazardous and will react in air. So that small size leads to large surface area and very different behavior. You also look at things like powder flow. Again, if you have that 10 by 10 by 10 block of aluminum, it's just going to sit there. But if you have a powder at, say, a larger size, let's say 100 micron, you can start doing things like fluidizing it, which can make transport or other processing easier. Quick application, because it's easy to present on a slide, really, is pigment hiding power. You have a pigment, in this case red, and you're grinding it down for use, and you want to say, well, how long do I grind? The longer you go, the more energy you need, and the smaller the particle size. And one approach is to take the pigment and make a test strip, and then paint a stripe like I show in these pictures at various grinding times, and evaluate, well, when is the stripe sufficiently opaque? Well, that really depends on your patience and how long it takes the ink to dry, or paint to dry, I guess. And then how skilled is your operator? And that can change from shift to shift. If you look at particle size distribution measured by laser diffraction, shown in the bottom, you'll see a pretty big change from the black of the original material as we grind finer and finer. And you'll see that the material under at 100 microns disappears pretty quickly in that first step, and then the material between 1 and 10 microns is going away more slowly. And it turns out there's a pretty good correlation between the geometric mean particle size and the hiding power, in this case is percent of target specification. And so you can, instead of relying on hiding power measurements to determine your grinding time, you can do particle size measurements. And this does a couple of nice things for you. The biggest is it gets you a very quick answer as to when you can stop your process. It also lets you take your skilled operators and ask them to do other more skilled work than watching paint dry. So kind of wins on all sorts of areas. You get better reproducibility, particularly with a number of operators. The core principle in laser diffraction is we investigate a particle with light to determine its size. And more exactly, we're going to look at the scattering as a function of angle to determine particle size. Let's back up a second and ask ourselves what happens when light strikes a particle. There are various ways of looking at it, and one way that's kind of easy to wrap your head around is you'll have a reflection shown in red here as it bounces off the surface of a particle. The particle can act as a lens and bend the light going through it. The particle can absorb the light and then re-radiate it. And that could be a fluorescence phenomena, or it could be simple fluorescence and absorption and black body radiation. But mostly we could think of that in terms of scattering, in terms of just the absorption, and then the diffraction for larger particles at the edges. So what this means is, depending on the size of the particle, these effects vary. And so if I can measure them, I can extract the particle size. For small particles, you will want to know what's happening to light inside the particle. And then there's a simplification I'll mention later. If the particle is large enough, you can kind of pretend it's opaque and just absorption happens. So going into the mechanics of an instrument, and this is a optical diagram for the HORIBA LA960 laser diffraction analyzer. We have a laser on the right, a lens, and we have a sample in the middle, and we have a flow cell, and that could be either particles falling or flowing in a liquid. And then we have detectors scattered around the sample. And you'll notice it goes over a wide range of angles. And then we have what's called a ring detector for very narrow angles in the forward direction. And so really what we want to measure is the scattered intensity as a function of this angle. So that's the mechanics or the physics of what we're measuring. What we get is a diffraction pattern. So I show here a cartoonish light bulb, a cartoonish particle, and then you'll see a diffraction pattern. Most of the light's coming through the middle. And then you'll see, in this case, rings with little peaks and valleys. Part of the complexity of that pattern reflects the complicated nature of the particle. When we're doing practical laser diffraction measurements for particle analysis, of course, we have particles with lots of different shapes, and they're all tumbling. And that tends to smear out these peaks and valleys, and so you get rings in your scattering. And so if you come out of the X-ray world, you'll think about that as kind of a powder diffraction pattern, except I don't have a regular crystal structure, which makes analysis a little bit different. So why do we have these diffraction patterns? And to talk to you about that, I have to talk a little bit about light. So light is basically an oscillating electric field and an oscillating magnetic field. And here's a neat cartoon showing electric field going up and down in both space and time, and its corresponding magnetic field in blue. We're just going to look at the electric field, and I want you to notice something about sines and waves, which is if I add two waves that are in phase, like this red and this blue on the top, I can just say, okay, that's double the amplitude, twice as far down, twice as far up. So I just add these up point by point, and you can see I have quite a large resulting wave amplitude, or quite bright light. So these two waves sum neatly, and then I get high intensity. You notice here with the red and the green, these waves are out of phase. And so now when I add these up, this is negative, this is positive, it adds up to just about zero. This is positive, this is negative, still adds up to zero. So the resulting sum is a wave with a very low amplitude, or quite a weak signal. And so I can measure the amplitude, that's really the intensity of the light with the detector. And to split hairs, I measure the square electric field of the electric field amplitude. So where do we have this difference in the waves I add up? And here I have to introduce path length difference. So if I have light coming here with these bubbles, they're supposed to be semicircles, but now I've mentioned they look like bubbles, and it's marching to the right. And then I look at it from a detector, say in the bottom right corner, and I say, okay, well, what wave am I getting from this point and this point from scattering events? I'm going to add this wave with this wave, and my detector is right at this plane. And so I have a difference in the path length depending on the angle. So you can see here where the arrow is kind of hidden, there's a little triangle that's made, and I get that path length difference. So as that changes, I'm going to get peaks and valleys and in the intensity with angle. Well, you really can't go from practical scattering data back to a particle size and shape the way you might do with the diffraction data from, say, a protein crystal. And you really can't invert scattering data very well. So we use optical models to interpret our data and understand the experiments and measurements. And there are really two big models. There's the Fraunhofer model, which has much more straightforward math, although you may quibble with that when we get further into what Fraunhofer entails. It treats your particles as large, opaque, two-dimensional disks. So we only worry about what's happening at the edges. These days, I only use this model to develop intuition about what's going on in my scattering system. But really, the proper calculation is the Mie calculations, generated about the same time. Now we're treating the particles as three-dimensional spheres, which makes a big difference, much more accurate. And we also notice what happens to light inside the spheres. These calculations are very messy, so I let the computer worry about that part. So the Fraunhofer approximation, which comes from this two-dimensional treatment, is you have a scatter intensity proportional to incident intensity, a size parameter called alpha, which is pi d over lambda. That's going to come up a few times in this talk. Then the first order Bessel function divided by of alpha times sine theta, where theta is your scattering angle, divided by alpha sine theta, and you square that. This is the easier version of the theory, and we're already into Bessel functions, so you can see where things go. The key takeaway on this is that there's a parameter called the diameter over lambda, and that's going to come up again, and that affects how you design instruments. The limits of Fraunhofer are that you really need to have large particles, more than about 40 wavelengths of light. So that says particle size is large, about 25 microns, then the Fraunhofer gives good results. If the particle is smaller, you're much better off with Mie. And in fact, even when the particle is larger, you're better off with Mie because it returns better results for wider angles. So to develop a little bit of intuition here, I plot scatter intensity on the left as a function of scattering angle, or log intensity as a function of log scattering angle for Fraunhofer. And you can see for the blue, that's a 50 micron particle, and the first order peak is at about 1 degree. And then for 100 micron particle, so larger particles, my first order peak is at a smaller angle. I think it's about 0.7 degrees. And so this graph tells you why some of these instruments can get so heavy. We need to measure very narrow forward scattering angles, and that means that we need a very stiff optical bench. And so one approach to making a stiff and long-lasting optical bench is to add more metal. It works quite well. The only time you worry about that is when you go to lift the darn thing up. So anyway, think of this graph when you try to lift up an analyzer, and you understand what's going on. The other is, I now mentioned kind of a rule of thumb, larger sizes, smaller angles. Another cartoony way of showing it, large particles, I have a strong scatter intensity and peaks at small angles. And with smaller particles, I have a kind of a wide scattering pattern and lower scatter intensity. Moving on, I promise you Mie scattering is messy, so I'll show you a quick picture with 3 blue circles. You can ignore everything else except the blue circles. The harsh part of this are actually these sums for S1 and S2. They tend to converge slowly. These are generated out of Riccati-Bessel functions, and those you can actually calculate in a civilized amount of time. You see numbers M and X, M times X, and theta. There's our friend X again, which I showed as alpha before, which is pi d by lambda. That says, once again, our results depend on the ratio of particle diameter to wavelength. If you want to measure smaller particle sizes, decrease the wavelength so that the particles kind of appear bigger. That will just make everything a whole lot easier. And you'll see this implemented in instruments. So if you look at the LA 960, which gets us to the smallest particle sizes, you're using a blue light source for the smallest particles in addition to a red light source. We do need to know relative refractive index, and that's the ratio of the refractive index of the particle to refractive index of the scattering matrix. As this goes to 1, the scattering declines to 0. So if you have something like glass particles in toluene, the refractive index of both is just about 1.5, and you have very, very weak or no scattering signal. And then as that ratio gets larger, you get stronger signals. And then finally, you have scattering angle. So when I say refractive index, I'm going to really talk about the complex refractive index. Some of these equations are much more easily manipulated when you use complex numbers. And so that's why we do it. So on the left, I have electric field coming in as that's the wavelength of light in air. It hits the particle, the wavelength inside shifts. So that's the real part of the refractive index. And then the amplitude goes down by absorption, and that's the imaginary part of refractive index. And then we get some light out the other end of the particle with some amplitude, and it could be just about 0. So if you think about something like a metal, this imaginary term is quite high. Comment on blue light and what happens as I change my light source from red at 650 to blue at 405. I plot on the left the normalized scattering intensity. I just put everything to 1, and then as a function of scattering angle for a fairly small particle. And I forget what number I used. I think it was 50 nanometers, but I can't remember offhand. But you can see the change in the scattering for the same particle. With the red light, it goes from a high of 1 to a low value of 0.89, about 11% change. But with blue, it goes from a high of 1 down to 0.75, which is a change of about 25%. And that change, or anytime you have a signal and you see signals and changes in signals, that gives you information. And so that larger change of 25% is giving us much more information about the particle than you get with the red light. Another comment is if you start looking at those numbers carefully, you realize that, hey, if I want to get my scattering and measure changes on the order of 10%, I really need to make sure I have my background stable with the 1%, the scatter signal. And so that's going to mean things like small changes in the optical design, avoiding narcissist effects, for example. It's going to mean making sure all your glassware, your windows are precision windows, and so on. Okay, moving to a few results. And I should back up and say that I blew through the math fairly quickly, deliberately, because I really let the machine do it most of the time. And certainly anytime I'm doing a series of measurements, I don't think much beyond rules of thumb for scattering. I don't need to. That's our software takes care of that for me, and it's a great relief. So let's get some example results. These are latex stearins at 30 nanometer, 40 nanometer, 50 nanometer, and 70 nanometer particle sizes. And by diffraction, and these are diameters, by the way, we can extract these smaller particle sizes by taking advantage of the blue light and the stable optical bench. Quick comment on effective size. Here I show 1 micron, 10 micron, 100 micron for comparison. And there are a couple things I want to mention here. One is this rule holds. These are Mie scattering calculations, and so I include the particle refractive index and the medium refractive index, just so I remember how I did it. We calculate out to very wide angles, and then we also see that this first order peak, that relation holds. Small particles, the peak keeps moving to wider angles. What happens if I'm mixing? One thing about that, with the Mie calculation, you can go out to very wide scattering angles. With Fraunhofer, you can only use data at narrow angles. Well, if you're mixing particles, just add the scattering patterns. So I have green from a 1 micron particle. I have black from a 2 micron particle. And I can make a weighted sum depending on the ratio of 1s to 2s to see the scattering pattern from the mixture. So you can see how the value in the 1 micron kind of cancels that first order peak or makes it weak for the 2 micron. And then doubles up the second order peak between 1 and 2 micron. And so you'll see a different set of peaks and valleys. And so I can use that information to extract the size distribution. Because most real samples, in fact, nearly all real samples, have a range of particle sizes. There's a comparison between Mie and Fraunhofer. I'm glad I remembered to include this slide, where you can see at wide angles, there's a difference between the red calculation, which is the approximation, and the exact blue. You can see how these wider peaks shift in position. And that gets important when you're calculating size distributions. Small particles, those differences become more pronounced, even at 10 microns at much earlier scattering angles, at much lower scattering angles. So let's say you're going off to measure glass beads, and this is a glass bead standard, and with a size of about 15 microns. And if you measure it using a Mie calculation, we actually get the right answer. So if I take the data and I feed it back in order and use Fraunhofer, I'm going to get a bimode in my size distribution, which is not real. I mean, I know that because I know the sample. And so once I've gone below this, this 25 micron limit, I really want to make sure I have the right calculation. CMP Slurry, another nice clear particle that really gives you fits. First off, it's a 150 nanometer particle, and so you're well outside the range where your approximations are supposed to work. And as expected, you get the wrong answer if you use the wrong model. So I'm interpreting this 15 micron as a 2, 3, 4 micron size particle. Generally a bad day when you make those kinds of mistakes. Now I mentioned the summation, and what we're really trying to do mathematically is go through, you have a scattering pattern and you're trying to find the distribution. And so if you imagine each point of the distribution as being an axis in a multidimensional space, you're searching an 80-dimensional space to find the right distribution. That's not a particularly easy math problem. There are a few approaches to solving it. Generally, they're all iterative, but you're basically going to start with the initial measurement, estimate distribution, back calculate what scattering you expect from that first estimate, find your error, and then calculate a new, more refined distribution, calculate the difference, and you go back and forth until the measured scattering matches the scattering calculated from your candidate distribution. So you'll see software taking various approaches to handling these calculations. Generally, you'll want to kind of turn off the automated approaches as you lock down a method. Other things that can affect your results, size, shape, optical properties of the particles will also affect the angle intensity of scattered light. So optical properties is really refractive index. We've kind of gone through that a little bit. Size is what I want to take advantage of. And then shape, some of that goes away because you have the particles tumbling. Some of it you still pick up because rough surfaces tend to cause more absorption, which causes really a larger effective imaginary term. It's extremely difficult to extract shape information without some a priori knowledge in particle analysis. And there are a few reasons that drive this. The first and strongest is most particle samples don't all have the same shape. And second, most instruments, including ours, do not do anything to align the particles. And so you can't really get that analogy to a single crystal diffraction pattern you can get with, say, X-ray diffraction of proteins or crystal structures. So we do assume a spherical model. It's very important to keep in mind as you start comparing with other techniques. I didn't implement this into the quiz, so I'll just give the answers. What particle shape is used for laser diffraction calculations? Hard sphere, cube, triangle, easy sphere. I'll give you credit for either hard sphere or easy sphere, but it's important just to keep that in mind as you try to understand results. Moving on to the practice of the measurement, really you start by preparing the sample, and really good sampling and dispersion is necessary. Otherwise, the instrument will measure what you put into it, and if you measure a sample that is flocculating, which is shown kind of in this, I guess, bottom left in the flocculation, it's going to measure the size of those groups of particles. So you need to make sure that your sample is a reasonably stable suspension. We don't have any flocculation or coalescence. Creaming and sedimentation we usually take care of in laser diffraction by mixing. And this is an advantage of laser diffraction over, say, dynamic light scattering, and you really can't mix a sample during a DLS measurement. Let me phrase that more carefully. You can mix, you'll just get the wrong answers. You then prepare the system, and this is the much easier step because you press a button to align the system. Typically, they align and then blank in the same step. Blank is really to measure the scattering background. That scattering either any stray light that's still left in the optical system, or scattering from your pure liquid. So there is very weak scattering from water and somewhat stronger scattering from organic solvents. And you want to subtract that off and just look at excess scattering. The modern systems all handle that quite easily. Just press a button. Unfortunately, we don't have a button press for adding surfactants or choosing surfactants. You then add the sample to the concentration range. And so generally you'll track concentration by looking at transmission. And you'll see that red bar in this left graph will move up towards a target range. You'll pump the sample through the measurement zone. And by you, I actually mean the machine. And there might be a final dispersion with an onboard ultrasonic probe, depending on instrument and depending on sample. You then press the measure button and the answer pops out. Now for sample types, you actually have a wide range of options. So you can look at dry powders with a dry powder feeder on the right. This is really a hopper. So you have a funnel, gravity feed. This vibrates and the particle goes off the edge, commits suicide down into the measurement area where air dispersion will break up some loose agglomerates, and then you'll make your measurement. For liquids, we have various sizes, depending on the amount of material you have, from 10 ml on up to hundreds of milliliters and auto samplers. So one thing when you're looking at a system is you want to make sure that you have sample handling that's appropriate for your sample. And you may find that running dry powders is a great idea because it just saves you a step in dispersion. Or you may find that you only have a tiny amount of material and you want to have the smallest cell volume possible. So how much material you need? It depends. And that's a pretty common answer from a lot of questions. Larger broad size distributions require larger sample volume, and then it depends on the size of the particles, and then it depends on the sampler. So I can use a small volume sampler to use less material. So here's a biopolymer, 100 micron diameter. I need 1 milligram, 1.3 milligrams. Colloidal silica, now we're at 35 nanometers. So this is really tiny stuff. I need 132 milligrams. So I need much more material for this much smaller particle. Here's some Mg Stearate, median size of 9.3 microns, need 0.16 milligrams. And I think the difference between the 114 and the 0.16 is our choice of sampler. On the dry system, we had a couple guys in the lab who had a big rivalry about who had the best method for the tiniest amount of sample. So kind of bets were made, and we actually got down to less than 5 mgs and pushed that method out to our customers. So that's quite a bit of fun in terms of measuring tiny amounts of dry material. So determining a method, which is really what drives that sample prep, can be exciting. And really, the reason you pay attention to your method is once you're running it over and over, you want to make sure you always get to the same answer for the same sample. Determining particle refractive index, and there are a few methods for that. And we have some webinars on that. We usually present them at various points. Choose your diluent. Are you going to use water? Are you going to use do you want to use a surfactant? Do you want to use hexane because your material is water soluble, or alcohol because it's cheaper than hexane, and so on. And so this diluent choice and surfactant choices is kind of tough to automate. So that goes back to understanding your particular material chemistry. You'll select which sampler. How much material do you have? Is it really, really precious, and therefore you're willing to put in some extra effort into a small size sample cell? Is it you have lots of material and you run a lot, so you want something that cleans itself? So you have to make that decision. Pump and stir settings, and we have software that will actually walk through each of those and help you select which is best, or you can do it manually. Same with concentration choice. And so you'll probably do a series of measurements in order to justify each of these, particularly if you're going to use this method over a long time and you want to make sure that your measurements are staying the same. And really what you're trying to do is reduce the sensitivity of the results to the method. Measurement duration, although in the modern system, that's not typically an issue. Do I need ultrasound? Okay, again, you might try various values of ultrasound to choose the best. And you really want to disperse the sample but not break the particles. And you want to check and make sure it's reproducible. Determining refractive index, that kind of first step in your method development. You can, really the best way is to go find a real component with a literature search or web search or Becky line test and so on. You can then measure the sample, recalculate it with different imaginary components to see how the results change, and choose a value that minimizes your R parameter or difference between your calculated distribution from your measured. And so you find the minimized value of that, and that gives you the best imaginary refractive index for a sample. And so you might do that if it's unknown. You can do that for real refractive index as well, but it's so easy to measure or estimate or determine otherwise. If you're going to be putting a long-term method, you want to make sure you have a right starting number. For concentration, what we typically do is make a plot like the one in the bottom left, where I have the transmission on the bottom, and then D50 is on the right, and I'll have a chi-squared or any other uncertainty parameter I want on the left. As the transmission goes down, that means I'm adding more and more material. Now, all the equations in laser diffraction work best when you only have one tiny amount of particles in your system. The trouble is that with tiny amount of particles, you only have a tiny amount of scattering, and that means your uncertainties are quite high. So you want to add enough material that your uncertainty, here shown by chi-squared, is going to fall down to civilized numbers. So you have nice reproducibility, but your size is not changing with concentration. So if I extend this graph out to the right, keep adding more and more material, eventually this flat line will start to either curve up or curve down. And so you want to make sure you operate in a regime where that line for measured particle size doesn't vary with concentration. And typically this is expressed in terms of transmission percent, because that's something easy for an operator to monitor. Ultrasound. If you have particles that are loosely agglomerated, you need to add energy to break them up. Sometimes mixing is enough. A lot of times you want to use more, and so you're going to just vibrate the liquid until the particles start falling apart. Typically our systems will set them high and vary the amount of time and look at what happens to the distribution. If I have an emulsion, I won't do this because all sorts of exciting things will happen as those sound waves go through the droplets, leading to confusion about results. If you're using ultrasound on a system, generally they tend to be weaker than these ultrasound you can get standalone systems. So you may use a standalone system to pre-disperse your sample before measurement. Now, one issue that you're going to have is that let's take the left-hand plot. If I look at particle size as increasing energy, or say ultrasound time, well, gee, I just want to add enough to start breaking up the loose conglomerates. And then once those are broken up, I'm going to have a region of stability where the size distribution doesn't change with applied energy. And it's great when you get that. Sometimes the universe is not so kind, and you'll see an actual plot that looks like this soft curve here. So what's happening is that in that kind of theoretical model, I have these loose agglomerates, I break them up, and I don't add enough energy that I mill my particles down to make broken particles. Because really, I want to make sure that my measurement is not a milling operation changing particle size. What tends to happen in real life is that as I add energy to break up agglomerates, I'm going to break up a few of the particles I want to measure. And that's why you'll see those softer curves. At that point, you're looking for reproducibility in your results. Analogous would be using air pressure with a dry powder disperser. And here we're using shock waves of air to break up loose agglomerates. So here's microcrystalline cellulose with 3 different air pressures. You can see the blue is high, and the purple and gray are medium and low. You can see the peak shifts finer for the high air pressure. So we're probably milling at that point. And so we're going to make our measurement either at mid or low air pressures. We do have software that will guide you through tests and will show results, and you can compare various values. The graph in the bottom here shows the effective refractive index on the R parameter and measured diameters. A couple bonus screenshots. If you click the measure button, the hardware makes the measurement, the software calculates the size distribution, and then you can actually dig in and inspect and compare the two to see whether the scattering from the calculated from the size distribution matches what you actually measure. If there's a big deviation, it's worth going and figuring out why. When your method's on point and your system is on point, then you're going to have nice, tight, reproducible results. This is magnesium stearate, run dry at 2 bar, D50. I have 4 measurements with a mean of 8.2 microns, a mean value of D50 at 8.2 microns, and a coefficient of variation of 0.3%. D10, mean value of 4.6, coefficient of variation of 0.24, and D90, 14.7 microns, coefficient of variation of 0.9%. So when things are together, you can, and this also, you're not using the same samples, it's good splitting as well. You get the same results over and over. Here's another result for cement, and I'll mention D50 is 11.1 microns. Again, we have that nice reproducibility, coefficient of variation, 2%, almost 3% on D10, 0.2 on D50, 0.7 on D90. That was run dry. When I run wet, my D50 value is still, it's now 11.7, and before it was 11.1. This really makes me feel good because it means that I'm measuring the same sample with 2 different dispersion approaches and getting the same numbers. So that points to both methods being good. Again, I have nice repeatability, 0.8%, coefficient variation on D50, 3% on D10, 0.6 on D90. A lot of our customers have multiple instruments, and so we've gone and tracked instrument-to-instrument variation. These are some glass bead materials with a range of sizes in the sample. You can get very good instrument variation on narrow size distribution samples like polystyrene stearins. I felt this was more realistic to present, so that's what I'm doing. These are 20 instruments, 5 different stearins. The worst case was D10 varied by about 3% on this 500 to 2 millimeter glass beads. Everything else, this is instrument to instrument. So you have one instrument in New Jersey and one instrument in California. You can expect them to have the same answer if you have the same sample and same method. Well, not just us that does these things. So these are 4 systems for industrial formulation. So our customer looked at mean size, D10, D5, D10, D50, D90, D95, and I have standard deviation, coefficients of variation. So the mean size across 4 different systems, 4 different labs, 0.5%, on D50, 0.6%, D5, 0.7%. So 1, we like this because it shows our instrument is doing well, and 2, it shows that their method is on point. And that's one take home, regardless of which system you have. When you do these studies, it's a good way to make sure every lab is treating samples the same. If we look at another formulation, we see similar numbers. That's shown formulation 2 in the graph below, 193 nanometers, D50 187, coefficient variation 0.8 and 0.3%. Okay, so hopefully I walked through some basic concepts in laser diffraction, how it works, what the system is trying to do, some of the things you'll encounter when making measurements. I like the technique a lot, but it's not perfect. There's some issues. The first that I'd like to remind people of is the volume basis by default. It's really good for thinking about things like mass balances and for saying, where is the bulk of my material? It does not do so well when you need to get number-based distributions. And so you're going to wind up finding kind of significant noticeable errors if you try to re-express laser diffraction data into number-based distributions. The second drawback that people mention is that there's no shape information, and that's true. And so and knowing that going in is certainly more useful than being surprised by it later on. If you do want shape information, you start looking at image analysis techniques. Well, the benefits, and a number of them, is the wide size range. So it measures from about tens of nanometers to 5 millimeters. And so I mentioned image analysis just a moment ago. Image analysis does not reach down below a couple microns. And so anyway, laser diffraction does. It has flexible sample handlers. So most kinds of materials can now be analyzed by a laser diffraction. And so you have a lot of options. You can buy a tool, you can add on more sample handling later on, as your needs vary. It's fast. It allows for very high throughput, and we have people who take advantage of that throughput to do a lot of analyses and improve their processes. It also means that when you're doing development, it's much easier to make the measurement than sit and have a theoretical discussion. Just put it in the machine and see what happens. Rather than try to figure out whether it's worth measuring or whether size went up or down, you can find out in real life. Laser diffraction is very easy to use. Modern instruments, lots of automation, lots of guidance from the software, and you get excellent precision, which means that you're not going to see a lot of variation in results that result in unnecessary investigations and downtime, which is important, particularly with a manufacturing process. And it's a first principle measurement, and that is that unlike microscopy, where I have an artifact and I compare the artifact to my sample, and here artifact will refer to a reticle or some sort of calibration steering. Laser diffraction, it depends on the wavelength and the geometry of the instrument, both of which are extremely stable. And we really just use the polystyrene stearins as checks on instrument performance. So if I put something in and I get the wrong answer, it means I made the sample wrong, or there's something wrong with the instrument, and we can go and fix it. And there is a huge global install base and history of laser diffraction. So as you start doing more work in particle analysis, you'll find out that most people know about laser diffraction as a technique, and so it's a language many people understand. And again, that ties back to some of these earlier discussions. I'm coming to the end, so keep reading our email newsletter. You can ask a question at labinfo@horiba.com. A question that often comes up as people start to wrap their head around this is, well, how do you find their best refractive index? And that will be one of the webinars in this series, how to do a refractive index study. Stay tuned, guys.
Alrighty. Well, thank you so much, Jeff, for the excellent webinar. For now, we'll see you guys all next time. Bye.